recording. I see that program from before break is not saved, so I will save it. Remember to do the same. All right, and as mentioned before break, uh, we will talk right now about edge detection and shape fitting. These are uh, different types of algorithms. Basically, what we are talking about today, uh, it's not related only to Aurora Vision Studio, to be honest with you. These are algorithms that's under different names with maybe a little different parameters, but you can find it in any machine vision software: template matching, region analysis, edge detection, shape fitting, code reading. These are really some basic building bricks, but I hope you will find our way to use them easy and fun. Okay, so let's open new image. Help tutorial show data directory as always. But from here we have to navigate. No, we don't have to. It's here. Count teeth. So help tutorial show data directory, count teeth, and drag drop saw blade PNG to acquire section of your program. Task here is to count teeth of this saw, and some additional task, a little asterisk task, would be to measure width of these teeth, just to check if any of them is damaged, thinned for some other reason. Uh, I will start with presenting a simple tool to detect edges of single teeth. Uh, but later on, we will do it in a little different manner. I just want to show you on very simple example, some basic parameters, explain how the tool works, and then we will use a little bit different approach to solve our task. What we need is scan edges. Maybe right now it's please only follow what I'm doing, and you don't have to do the same in your programs. We will do together final solution. Scan edges 1D. And as in majority of uh, this algorithms in our toolbox, we have multiple choices here. We can scan for edges, which is a single transition from dark to bright or from bright to dark. But what's important is that it is single transition. And we can, of course, detect multiple edges like this with a single tool, but the most important is that it is one transition, like shown here. Other option is to scan for ridges, and these are some very narrow stripes, uh, width about 1 to maybe 3 pixels, something very narrow, where we have two transitions. For example, if we have dark ridge, we have transition from bright to dark and from dark to bright, but these transitions are not possible are seen as a single object, single feature in this image because it's very narrow. That's what makes it different from scan stripes, where we are scanning objects that have two edges, let's say, like here, scanning for edges, single transition, scan stripes, two transitions. So we have two edges on the two ends of the stripe in two transitions of opposite polarity. So for example, bright to dark and then dark to bright, but the stripe itself can be wider. It would all make more sense why it's split like this if we dived into math that is going behind it to detect the edges, but I think there is no point in bringing so much math to this training. After all, it's about usage of the tool. So let's just select scan stripes single. I'm linking an image here, and I have to define scan path. Let's do it like this. Iterate once, and I will display my stripe and also in another section of my preview width of this stripe. Everything works well. Uh, I detected it with no problem. We will go through some most important parameters of this tool in a moment. But first of all, let's think about our task. Uh, if we were to scan each teeth in the saw blade, uh, we will have to create some circular path to count multiple stripes, to count multiple teeth. And this will be one of the tasks. And if we want to also measure the width of the stripe of this teeth, it is very important to measure this width at the same height of the teeth, let's say, because as you can see, uh, they are of quite complex shape, and if we want to compare one to the other to check which one is too narrow or too thick, we have to measure at the same height. So additional task here before we get to scanning stripes around the saw blade will be to create circular path that goes through the middle of every teeth. That we will do in a moment. For now, let's focus on the scanning stripe itself, on edge detection itself. Okay. Um, I did not mention it before, but many filters, many tools in our toolbox have diagnostic outputs. You can see them marked in yellow and with uh, beginning of the name, um, which makes it different from regular inputs and regular outputs. Diagnostic outputs are available only if diagnostic mode is enabled. It's available here, so we can turn it off. But by default, diagnostic mode is on. What I added to our preview right now is diagnostic sampling points. And it looks like this. What the algorithm does is to, in the scanning direction, so along our scanning path, which is like this. Let me just turn off this for a moment. Yeah, this is our scanning path. And going along this path, we are counting some kind of average brightness for the pixels in the same, let's call it column. And then brightness of these columns is compared one to another, and that's how the transition is detected. I am showing you this because of this parameter. In scan width, we can change how high these columns are. So if I increase this to, for example, 10, you can see that we are averaging much more pixels and comparing each column to the next one, searching for an edge. What does it mean? If you have very complex shape, um, and you are scanning for edges, it may be better to use smaller scan width because you don't want, for example, here, the transition, we can even check this, the transition should have smaller magnitude in this case because of scanning width is too high. Let's check stripe magnitude. Right now it's 30. If I go back to the stripe width of 5, it's over 50. So you have to keep that in mind. On the other hand, if you are dealing with a very weak edge, with blurred edge, then it may be good idea to use higher scan width. And of course, as with everything in machine vision, it's always good idea to experiment a little with different settings. Okay, let's go to another parameters of scan edges or scan stripes in this case. To explain some of them, I will show you a profile of brightness. This is how brightness is changing across this scanning path. And this is average brightness for the pixels in our scanning column, let's say. We can smooth uh, this profile, which in some cases will make detection more difficult because right now you see that transition between bright to dark and dark to bright, it's not as narrow, it's not as good visible as before when we had smaller smoothing or without smoothing at all. But in cases where we have a lot of noise going on around the edges, then smoothing may be really handy. Minimum magnitude. Yeah, so how strong the edge is, what is the contrast between brights and darks. We have also parameter called max inner edge magnitude, and this applies to stripes exclusively, um, because it affects any disturbance, any additional edge that may appear between outside edges of our stripe. So we can uh, assign maximum brightness here and avoid detecting some elements that appear between the edges of the stripe that we actually want to scan. Stripe polarity, dark in our case, of course, and we can also assign threshold to the width of the stripe. Uh, Stripe selection. In this case, we don't have that problem, but if we had more candidates for edges across our scanning path, we have option to choose first, last, or best. So uh, if there was an edge somewhere here in this white area at the beginning, and I would choose first as a stripe selection, then I would detect it here rather than here. Uh, Everything that we talk about here, first or last, is according to the scanning direction. Okay, I think that's quite enough here as for explanation how edge detection works in general. I think it's not that difficult, and we can move on with our main task. I will remove this from our program. Now that we know the basics, we can think how to create our circular scanning path and how to assure that it always goes in the middle of the teeth. My suggestion is to detect inner circle first, this inner hole in the saw blade, and use it as some kind of alignment for center of our scanning path. And this actually will be a task from shape fitting category. Computer Vision 2D in our toolbox, fit shape. And what you see here are different types of objects, segment, circle, arc, path, that we can fit our line, that's the shapes that we can fit. But what is also important that for each of them we have the same options as for single edge detection. So edges, ridges, and stripe, because under the hood what is going here in shape detection is the same as in single edge detection, only multiplied many times across our fitting field. So shape detection, shape fitting tools use edge detection as a primary algorithm. That's how it can be explained. Let's select fit circle to edges. I will link an image, and I have to specify fitting field. Double click on this input in fitting field takes me to the editor. And I have to do it like this. Please notice that this also, this fitting field has a direction. You see these arrows here, and it means that our scanning, our searching for edge transition will go from inside to outside of the circle. And in case of circle, this is fixed, I guess. Yeah, But if we were fitting segment or a path, then we could just turn the region around to change scanning direction. All right, so that's our fitting field. Let's see it on the image. Sorry. Okay, that's our fitting field. And let's put some diagnostic outputs to display. Let's start with diagnostic scan segments. What you see here, these are basically scanning paths looking for a single edges. So the same thing that I showed you before on a simple example with a stripe. This is single edge scan. Later on in the algorithm, this single scans points detected with these scans are used to fit circle. That's why these two types of tools, edge detection and shape fitting, that's why we are talking about it in the single example, because they are basically the same thing. We can change number of these scans, which will be very useful, especially if we want to detect small circle like this. Many points on the circle will of course help us to fit it better, especially if we consider that some of these scan segments may not return a edge. In this case, it's not a problem because we have edge of very good contrast, and we will detect edge point in every case. But on some weaker edges, there might be a case that some of the scanning segments will not give you results. That's why it's always better to have higher scan count. Let's change it, for example, to 30. And of course, as in the example with single edge scanning or single stripe scanning, we have also, I will decrease scan count a little for a moment just to show you what's happening here. This is the area where we average value of the pixels for comparison for edge detection. So it's the same thing as shown before in stripe scanning. We can also change that to make it wider or narrower. In our case, I will make it narrow as for 3 pixels. Okay, I think that's good. What else do we have here? Some standard parameters for edge detection. So edge transition, bright to dark or dark to bright, minimum magnitude, smoothing, edge selection, first, best, last. Some typical parameters, I think they are quite clear. Uh, I mentioned before that some of the scanning segments may not return an edge point. That's why we have maximum incompleteness parameter. So if 10% of our scanning segments do not return a value, then we don't want to fit circle in the remaining points. That's what it says. It can be also increased. So let's make it like this. And different mathematical fitting method. All right, I think that's quite enough of parameters and theory. Let's see how it works. Let's put out circle to our preview. And that's what you get. That's our inner circle. And now question is how to use it to create scanning path that will go across teeth on the outside of our saw blade. I will just resize this circle. I will make it larger. It will keep the same center, so it will be aligned with our blade. All I want to do is to make it as large so it can pass through the teeth. So link it here and new size. It is a new radius for the circle in pixels. So let's check how large it should be more or less. I think this is the right radius. 120 pixels. Let's try it. Maybe a little larger. Yep, I think that's good. So we will measure width of the teeth at the same distance of the saw blade center. And we will use scan stripes, so the tool you already know, for measuring and counting teeth. So scan stripes, but multiple this time. Okay, I linked an image. I need also scanning path, but if I try linking directly a circle, which has data type of circle 2D to in scan path, which has data type of a path, it's not working. There is no automatic conversion here. And we have to add one more thing in between. Create circle path. This is a tool to convert circle data type into path. Difference is that path has to consist of a straight segment. This is not curved line. Path will always consist of a straight segments. That's why we need to convert it ourselves. And if I would use default parameters like here, let's see what happens. This would be my scanning path because I have 8 points or 8 segments specified as the number here. So this function is trying to approximate my input circle with 8 straight segments, and that's too little. Let's make it larger. Let's make it, for example, 50. That's a lot better, and this can be used as a scanning path. Let's quickly check parameters of scan stripes. Okay, magnitude is good. Stripe polarity dark, that's correct. I think it should work well. Let's check. Yep, every single stripe was detected, every single teeth. Let's see our results. So the first part of the task was to count all the teeth. And we have output stripes count. I guess this is it. There is a question in chat why we did not connect out circle in fit circle, out circle and fit circle to in-scan path, in-scan stripes. First of all, because it's not possible. It's still the same conflict of data types. We have circle to D and a path, so it has to be converted with a circle, create circle path. And the other reason is that circle here is the small inner circle of the saw blade, and we had to resize it so that it passes through the teeth on the outside. Okay. And the other part of the task was to measure width of the stripes, and it's also available here, out stripes width, about 11 pixels wide. Okay, are there any questions to this example? Let's save it. We will do one more example for edge detection and shape fitting before getting to the exercise. I think you already know what's the idea here, to do something together and then for you to do some task independently. But in this case, there is another demo program. So new program and new image, help tutorial, show data directory. But this time we need to go to a different location, but it's easier to go there from here. Please go up 2 levels to Aurora Vision Studio Professional folder. And here, instead of going to tutorial, please go to examples. From here, blade and images, please drag drop this folder to acquire section of your program. So whole path to a folder with images should look like this. Sorry. Okay, so what do we have here? What kind of images are we dealing with? It may be even the same object as before, but we are seeing single teeth, single blade of the saw in a close-up. And the task here would be to measure angles here, this tip of our blade, and if possible, also here, to basically check uh, how if this blade is still operational, if the tip is sharp and it can be used. We will measure this angle, and also as an additional task, this one here. As you can see, and going through a few images, they are not exactly well positioned. They're more or less in the same orientation. Blade is more or less in the same spot, but not exactly. And that's why we have to find some fixturing first. We have to locate this blade, locate its edges in order to do some measurements. And the most typical choice for such a localization, for such a fixturing, would be pattern matching. That's most typical tool to locate object in a field of view. But in this case, it will be difficult because there is no fixed shape in our image that we could use as a template. Everything is a little bit shaky here. That's why we will stick to edge detection tools, to shape fitting tools, and we will do just fine using them. I will start with fit segment tool. Fit segment to edges. Make an image here. Double click on fitting field. And what I want to do is to detect this edge. Leftmost edge of our blade, which can move a little from left to right, a little up, down. That's why I have to specify my fitting field quite wide. Sorry, I will do it the other way around. Yeah, like this. I don't know if you notice that if you drag your scanning path one way, it determines scanning direction. And if you want the other direction, you can just flip it like this. Okay, I think that's good fitting field. Now let's quickly go through parameters. Uh, Edge transition should be the other way around, so dark to bright. And edge selection, it should be first because I don't want to detect some edge that appears here on the other side of our blade. I want first edge in this direction, going from right edge of the image to the from left edge of the image to the right. And maximum incompleteness, let's increase it to 0.3, for example. Okay, and what do we get? Very nice segment in this case on first image. Let's check a few more. Yeah, okay. It may look good at the first glance, but if we consider that we want to measure angle here, and then even small mistake in detecting this edge will have quite significant impact on our measured angle. That's why we have to do something about it. If I drag drop out edges to our preview and maybe even scanning segments, you see what's going on. We have 10 scanning segments, and these are edges that were detected based on these 8 points. In this case, we are fitting a straight segment. Let's first of all increase scan count, for example, to 20. More points for our approximation should improve our results. But let's also use outlier suppression. This option helps to exclude some extreme points from our fitting segment tool. So we can change different mathematical approach to this outlier suppression. Please test a few different, see what happens. And now you can see that this 2 or even maybe this 3 points were really less important for uh, for fitting this line. Okay, let's check again on different images. Yeah, this is some extreme example, but still, if we consider only edge detection, I think it went well. Okay, good. So we have first edge for our measurement, and what's also very important, we have some fixturing, we have some point, we have feature, we detected feature that is part of our saw blade, so we are able to tell where is it located in the image. To use this segment as a fixture, we have to create coordinate system based on it. So control space, and I will start typing coordinate system. Yeah, we have it here. Create coordinate system. And a few options to choose from. Of course, what we need is from segment. Yes, in order to run diagnostic tools, you have to enable diagnostic mode here. And this would be probably possible only when the program is stopped. If my program is running, I cannot change diagnostic mode. I have to stop the program and enable it here. All right, and so we have our fixture, our coordinate system, and we will use it to detect this top edge. I will use fit segment again. Image. But before drawing fitting field in editor, I will link coordinate system to fitting field alignment. Yeah. And now if I go to in fitting field, I see my fixturing, my coordinate system, and everything that I will do right now, this fitting field that I will draw, will be defined in this coordinate system. This coordinate system will move along our blade, therefore my fitting field will move also. I will still make it a little wider because yeah, you've seen how this leftmost edge look like. Our coordinate system is not very precise because the edge is also a little shaky. I will make this region a little wider. Maybe some good tip here when creating regions, if you just drag it by hand, it's sometimes difficult to do it precisely. If you press Control button, it will align better to main axis of your coordinate system. It's just easier to draw a straight line with Control button pressed. Okay. In terms of parameters, of course, we need dark to bright transition, and we need first edge. Let's also right away add outlier suppression and maximum incompleteness too. So the same parameters that we used for detecting leftmost edge, now we will use it for top edge detection. Adding segment to preview and iterating through images. Not so perfect, as you can see. Okay, we could discuss what is the best segment fitted to this line. It's not exactly straight, but I think we can do better. Let's see how the edges are detected here. Yeah, like this. I will increase scan count. Let's also check different outlier suppression method. It didn't improve actually. And how about scan count? Scan width. Yeah, that's better. So increased scan width allowed to fit this line more precisely. But of course, every change that we make has to be verified on different samples, on different images too, because it's very common that if we correct something on one image, we make it worse on others. So it always have to be tested. Yeah. So I will stay with scan width of 5. Okay, I think it's good enough. So now let's measure the angle. This is also something that's usually come together if you are detecting some edges, fitting shapes like circles and lines. And that's very commonly used in applications when you want to measure something, measure distance, measure angle, because we need these simple primitives like segments, circles, and arcs for measurement. And this is something that you asked also before, when to use geometry tools. Measuring tools are part of geometry 2D toolset. For example, measuring angle is one of the options here. Let's drag drop from geometry 2D, measure angle, and we have angle between segments. Let's test this one. Leftmost segment, so the first feed segment tool that we used, and the second. Iterate once. We can also change direction in which we are measuring this angle. So polygon counterclockwise, that's what I need in my case, but it all depends on the direction of segments that you have here, and direction of segments depends on the scanning direction. So if you did the same as me, scanning from left to right and from top to bottom, looking for edges, then you will probably have to choose the same option here. So polygon counterclockwise. And now, how about this edge? Because there's more difficult task here to measure this angle to find this corner of the blade. And we will create a new coordinate system. But first of all, let's find point here. Let's find intersection of these segments. Let's imagine that we are interpolating these segments to a lines and we are finding their intersection. And that's exactly the tool that we need, line to line. Not really. Line intersection, line intersection. That's it. Line and segment are formally also different data types in our software, but there is automatic conversion. So we can drag segment to a line input like this, iterate once, and get this point as the output. And now I will use this point, this intersection, to create another coordinate system. So create coordinate system from point this time. And this what I'm doing here is also quite important operation because sometimes to locate some object accurately in your field of view, to have some really accurate fixture for some later measurements, it's good idea to create multi-step fixturing. So you're finding one feature in the field on your object in a field of view that can be easily detected, but not as accurate as you would desire. For example, this leftmost edge was this element, but based on this, you can detect other features which will allow you to fixture everything more precisely. So building such a multi-layer fixturing is in many cases a good idea. Okay, so intersection point goes here, and this is our second coordinate system. I want to also assign an angle to this coordinate system because by default it is 0, so we will have fixturing in terms of x and y direction, but no fixturing in terms of angle. I want this angle to be taken from this upper edge, from the top edge. So it will be, sorry, segment direction. I also did not mention it before, that not all of the inputs and outputs of some different filters are available by default. Sometimes you have to right click on some output to see that something more is available. Or you can just go to show hide ports, and here you can also see everything, every output, every structure, every data that is available on output of this particular filter. And segment direction, meaning segment angular orientation, was not available by default. That's why I had to add it. And now I can link it with input angle of create coordinate system. Yep, now you can see that it is aligned. And I will use it fit segment method again, third time in this program. Or let's even copy paste. as you can see, our program is getting a little longer right now, and it's sometimes difficult to, or maybe not really convenient, but not difficult, to scroll through entire program to link inputs and outputs. That's why we can label some of them, and it will be much more difficult than especially something like input image, which we use in multiple filters and multiple functions in our program. Let's label it. Yeah, we can call it just image. We can also label a connection to make it clearer to view, to avoid drawing so many arrows, because after um, building quite extensive application, you will see that you cannot follow this efficiently. There is a question in the chat. Is it possible to employ coordinate system for guiding a robot arm in the precision task of picking and placing objects? Of course. Uh, Robot guiding is one of the most typical applications in machine vision in general, and precise object detection is part of the task. Um, to think if we will use create coordinate system or not, that's a marginal point, I would say. The most important is that we have the coordinates. So even we don't have to use create coordinate system block, even using line-to-line intersection outputs coordinates. So locating object is part of the task, very important. But the other part of the task of robot guidance is calibration, because yeah, that's probably why you are asking about coordinate system. Camera and the robot have to live in the same coordinate system to exchange data and for everything to work well, to make them understand that's X and Y location for camera. What does it mean for the robot? It's the same X and Y. They need to exist in the same coordinate system. And that's why we need to calibrate the camera and calibrate robot. And I will show you how to perform calibration in the next section of today's training. Uh, Let me check. I think it will be today, but let me just check our schedule. Yeah, I think we will manage. We have one more thing to do before, but I think we will get to calibration today. So locate the object, calibrate the camera. I will show you how, and calibrate the robot. Then we can guide robotic arm to do some simple pick and place operation. Okay, so we need an image, and I was doing labeling. Okay, let's label this connection too. Yep, you can see that now it looks a lot better. Coordinate system and that we created here based on this tip point will be used as a fitting field alignment. And our fitting field will be somewhere here. I will make it quite narrow. Another question in chat. Will we go over communication of Aurora Vision with external devices like robotic arm? We will go through communication tomorrow, uh, but it will not be specifically for the robotic arm. Uh, I will present some very simple tools for TCP/IP communication, which I guess it's very universal and can be used also to communicate with robots. But if you would like to use some other means of communication, I will just point you in the right direction, show you where to find different filters, for example, to use discrete IOs. If you would like to use some industrial protocols like Profinet, Ethernet IP. We don't have that directly in our software, but you can use communication cards that have this option, and then you're communicating, for example, via TCP/IP with communication card, and communication card is set to communicate, for example, with a robot via Profinet. That's how it's done. And that's how TCP/IP communication is very important, and we will cover it during tomorrow's training because it's just the most widely used and can solve majority of applications, I guess. Okay, so this is my fitting field, and let's see how it works. Not very good right now. Let me check. Direction is like this, so dark to bright. But the problem is edge selection for sure. I don't want the first edge. It looks like this because we detected some points here. I want the best edge in this case. Yeah, that's better. And let's check a few images. That's also not good. I think in this case, that's strange. Yeah, different outlier suppression method gave better results. Okay, this is also a problem. We have some scratches on the blade, and it caused our segment, our edge, to be located not in the right place. So maybe let's add some smoothing. Yeah, that's a lot better. I think it's quite robust in terms of detecting right edge, even so that this is not that simple task for edge detection. Uh, we have low resolution, we have some scratches and other noises in the image. Edge is really thin, really short, I should say, probably, and still we are getting some good results. So what is left to do is to measure angle again. So angle between segments. and I want top edge, so this segment and this segment, arc, yeah, this time, again, polygon counterclockwise, it's good method. What else we can do here, because there was one case where the blade was practically non-existing. Yeah, here. And okay, yeah, that would be detected with angle measurement, because everything is upside down here. Our segments have different directions, and that's why this angle, this arc, is completely different here. But just to be sure, we could also measure distance from one segment to the other. So from leftmost edge of the blade to this rightmost edge of the blade, the small upper edge. How to do it? Distance. Sorry. Let's take it from here. Geometry to D. Measure distance. Segment to segment distance. And I will link leftmost segment with last one, right segment. Yeah, as you can imagine, in a final application, I would also label this. So this would be because the longer, the more complex program is, the more difficult it is to really remember and know which output was, what was the meaning of each output. So let's label this also its top segment and the right segment. All right. Yep, and now you can see measured distance here. Value of this measurement, let's add it here. So this is our distance, 36.5 pixel. Yep, and almost nothing in this case. Are there any questions? Of course, I will save this program. Edge detection, shape fitting. Okay, it can be here. And now it is the time for an exercise. So new program and new image. Help tutorial, show data directory. And gasket inspection. There are a few images here. Let's drag drop entire folder. And what I would like you to do, oh, maybe let me show you. Okay, that's a screenshot from solution for this exercise. Uh, what I would like you to do is to measure angle between these two circles. So line connecting center of this larger circle with the centers of these two outside circles. We have two segments like this, and I want this angle to be measured. That's one task. The other task is to measure distance between this line, leftmost line of the gasket. We are not considering this element. It should be excluded from our fitting line. So we want this average left line to measure distance from centers of these two circles. So at the end of the day, at the end of this exercise, I would like to see measurements for the angle and distance for two circles from the left edge. I will leave it here just for you to check. And it's also some hint on how to approach this. And I will leave you with this task. I think maybe 15 to 20 minutes because it's a little more complex. And after that, I will present a solution to you. Please write any questions in the chat. I'll be right back. And how is it going with our gasket measurements? Please let me know if you are stuck at any point. Please remember also that there are more images in the folder, and the gasket is a little misplaced in a field of view. Distance between two circle. Maybe I will read whole question. I don't know if you are following the chat. What feature is used for the distance between two circle midpoints? I found the distance, uh, but only the one that measures edges. Uh, Actually, you don't. Yeah, if you choose circle to circle distance, this will measure shortest distance between the circles, so from edge to edge. And what you need is from center to center. You don't have to measure circles in this case. You can measure point to point because you have coordinates of the circle center. I will start building this solution here. You can just watch and follow me, or you can continue with your own and compare later. First thing that we need to do here is to find a fixture to locate the gasket in the field of view, and I will use template matching for this purpose. So I used locate object edges to locate our gasket. And as a template here, I am not using entire object because it's not necessary. I just chose some very characteristic part of it whenever I can find this small part of our gasket. Uh, I am sure that I can find all the other parts because they are in fixed position. And now with this fixture, I don't have to create coordinate system because it's already available as the output of locate object edges. You have out object alignment. That's what you can use as a coordinate system for fixturing any other tools to your pattern. Because this tool is mainly used for this purpose, that's why it's available directly on its outputs. Okay, so now I need 3 circles, 2 smaller ones and 1 big circle here. So fit circle method. Fit to edges like this. And out object alignment is connected to in fitting field alignment. And let's label this connection too. Yeah, and now there it is the part that you were asking about. I need to create segments between circle centers and just to measure angle between these segments. And one of the problems here may be that circle center is not visible by default as this filter output. So I have to right click on out circle and here select center. And now point to point distance. Let's also label it from here to here. Okay, and that's our segment, and the same thing with bottom circle. So we need this one, and we need this one. And now finally measuring the angle. Yes, exactly. I see a valid solution in chat. And I see also another question. What is the purpose of region of interest on the left bottom? No purpose at all of this region of interest. This is also to notice that our pattern is located, because that's that's the bounding rectangle of my template that I used in the first step. And I placed it on a preview just to be sure that my template, my pattern is located, but I am not using this rectangle at all. What I am using for the next tools is this alignment here. And yeah, it's moving with our gasket. So this is our angle, and now I need to detect this leftmost line of the gasket with fit segment filter. Okay, and to measure these two distances, I will use point to line distance. This is my line, so automatic conversion between segment and a line. And I need two circle centers. Okay, that's the first one. And measure distance. And the second one. Okay, program is saved. Please let me know if there are still some open points for you in this application. Something is not clear, something is not working exactly as you would expect. Of course, we have to check every image in the data set just to be sure that it is working well. Uh, do you need a break? Because according to what I planned for us today, we have only calibration to talk about. So the question is, if you want to have a 10 minutes break now and talk about calibration after, or do you want to go straight into the calibration topic and maybe finish just a few minutes earlier? A break will be great. Okay, so see you in 10 minutes. Yeah. Okay, I hope we are all back after this short break. If you have any additional questions to the previous exercise, please let me know. And if not, we are getting into another topic, calibration of the camera. What does it mean and why we do it? Uh, Previously, uh, there was a question about guiding robots, and this actually is a valid question for guiding any other external device, for example, laser marker, or I don't know what else can be guided by a machine vision, by a vision system. But yeah, if we are able to locate some objects in the field of view, and if we are able to calibrate both devices, camera and guided devices, in the same coordinate system, then we can do it. Uh, Other reason to calibrate camera is to measure something in the real world units. When we created our measurement in previous example, all measurements were done in pixels. So we don't know how many millimeters there was, how large the gasket was. Um, if we want to measure in real world units, then we have to calibrate too. There is also a third possible application for camera calibration when we want to uh, get rid or minimize influence of distortion and perspective. In this, actually, I recommend to calibrate using calibration grid in every case. There are also different methods, simpler ones. If what we need is only to convert pixels to millimeters, then probably we can do it by implementing simple mathematical operation, to have some multiplier, to have some factor by which we change our pixel measurement. But it's not very precise, and I recommend just whenever you need to calibrate for whatever reason, to use calibration grid. And calibrating on a grid also allows us to, let's call it, straighten up the image. So if camera is looking at our field of view, at our space at angle, then we can get rid of this perspective and make it look like straight look down. I think you know what I mean, and definitely it will be clear once we do it. So three possible applications where calibrating camera is necessary: guiding external device, performing measurement in real world units, or removing distortion and perspective. And removing distortion and perspective, there are also some other algorithms to do it, but calibrating on a grid is very good method, and I think we can focus on that one. Okay, for this exercise, I will need to share images with you, because I will capture images of calibration grid here with a live camera, and I will share it with you in OneDrive folder. This is, I know it's, if it will be visible. Yeah, this is our calibration grid. I will put it under the camera right now. And I need GigaVision grab image. Okay, and address. As you can see, we have board with circles, and there are different types of calibration boards available. And there is a checkerboard calibration grid, and if we have circle boards, there is symmetrical, like this one, or asymmetrical, where circles are placed at diagonal one to the other. I hope you can imagine that. The most important information here is that in Aurora Vision Studio, in our software, we support symmetrical calibration grid. So checkerboard is okay, circle board is okay, as long as it looks like this one, not with circles at diagonal. Okay, let me just correct one thing. I will take a few images of this grid because why single image is not enough. Uh, Calibration grid should cover entire field of view. Uh, of course, if I captured only single image and calibrated basing on that, it would also give me some good results, but they will be better if calibration grid covers entire field of view. I can do it with a single calibration board large enough to cover an entire field of view, or I can capture a series of images with calibration board placed in different areas in the field of view. And that's what I am going to do. But first of all, let's make sure that quality of our image is good. I will make it a little brighter, and I will make it by changing aperture on my lens. Oh, sorry, that's focus. So first of all, I will open lens aperture, and then I will adjust focus. Okay, I think it's fine. And let's save some images. There are some, our calibration will not be extremely accurate because, as you can see, this is just a printed sheet of paper and it's not exactly flat. And of course, precision of printed calibration board, it's has also some limits. But I think it will be just enough for our purpose. Mm. Okay, I think that we have it for images, uh, and on this four images combined, calibration board should cover entire field of view. Uh, let's stop here for a moment because we have to talk about calibration process and the steps that it will take. First step of calibration is calibrating a camera. Um, it means calibrating camera intrinsic parameters. There are intrinsic camera parameters and parameters that are related to station, to perspective. So this these are actually separate calibrations. These are two separate steps which can be done independently. So first step, calibrating intrinsic parameters, is about calibrating lens distortion, calibrating everything that is related to camera as device itself, and it can be done uh, even in different place. It camera doesn't have to be mounted on the actual working station. You can calibrate this first part even on your desktop. The most important for the whole operation is calibrating perspective and real world units on the station later on. But these two steps are independent. So you can calibrate camera parameters first, later mount your camera on the actual station and continue the process, calibrate perspective and real world units. That's why I will change location of my camera. I will misplace my camera right now to present to you that it's independent. We will have different position of the camera for these two stages of calibration. Okay, okay, I think that's good. Let's adjust focus once more. And now I will I will save only a single image, which we will use to calibrate perspective. Let me now add these images to our OneDrive. Okay, it's already there. So you can go to OneDrive linked in the chat and go to Programs, Calibration, and download these two folders with images. Do you have it? Or are there any problems with accessing OneDrive? Okay, please let me know in case of any problems, and let's move on. There are a few ways to approach camera calibration in our software. Process is as I described before, so we have to calibrate camera intrinsic parameters, then rectify image, calibrate perspective as a second step. And then we can make use of this calibration. We can transform some of the objects in the field of view from one coordinate system that is in pixels and it's not calibrated to the real world coordinate system to make some measurements. We will do it also. But let's start with the calibration process itself, and we will do it in the easiest possible way by using rectify image block. Uh, we need some input image here, but what kind of image is it is not really important at this point. I will use image with the perspective. So in our training folder in calibration, I will use the image from perspective calibration folder. So I will drag drop it here and link to our rectify image. But it does not matter much because that's only the image that will be processed, that will be transformed by this calibration. What we need to do first is to prepare rectification map. And if you double click on in rectification map, a new calibration editor will appear that will guide you step by step through all of the process of calibration. That's why this approach with rectify image filter is the easiest and most convenient in my opinion, because you can, instead of using this editor, instead of using this wizard that guides you step by step, you can do everything by hand. You will need to use different filters for it. I will show you which one are these later on, but I think it's the easiest just to follow this editor instead of programming everything by hand. So we see three steps in calibration editor. First is camera calibration, so exactly what I meant before. And we can add images for calibration here. We have this little folder icon, and let's navigate to camera calibration images, and let's upload all four. Now we have to specify what kind of calibration board are we using. So it's circles. What is circle radius in pixels? And that can be measured. We have measuring tool here. And let's measure a single circle. It's about 60 pixels diameter, so 30 pixels radius. This value is not used for calibration. It will be used by the algorithm to detect circles, to detect this calibration points. And the points that will be detected will be used for calibration. So you don't have to be that precise in this measurement. Okay, threshold for edge detection, because what will be done here is edge detection for all of these circles, and I see that my image is quite dark, so I will decrease it, for example, to 10. And now I click locate. And as you can see, on each of the four images, my circles were successfully located, and by this greenish area, you can tell which area of our field of view is covered with the calibration board. So yeah, it's not like full field of view. There are some margins that are not where my calibration board was not present, but it's not a problem. Just in this green area, results are based on calibration. In this area where the calibration board were not present, results will be just extrapolated. So it's still good. Probably it could be a little more accurate if I placed calibration boards more precisely at the edges of the field of view, but this is not a problem. I think what we see here is completely good, completely valid, and we can go on. We have some camera parameters here, and this is type of the lens. Pinhole, standard optics, or telecentric lens, which is the type of lens which reduces to minimum perspective distortion. You can Google it if you don't know how it looks like and what it does. I recommend to do so because it's really fun and interesting to check what is telecentric lens. But for us, the most important is that we are using pinhole option here, because we have standard optics. We can also input focal length of the lens. We don't have to do it, but it will be easier and better for the algorithm. Um, Results will be more precise if we specify lens focal length. Let me check what is it in my case. Okay. In my case, it's 16, but in pixels, that's strange. Okay. Probably you can find all this data in camera datasheet and lens itself, but let's leave it empty like this. Let's leave it on auto. We have also different types of distortion correction here, but let's leave it on a polynomial also. And once we have all the parameters and once we have our calibration points located, we can compute camera calibration model. Red arrows that you see here are graphical display of the calibration error. And yeah, that's what you see here is caused by my calibration board not being exactly flat. It looks like the error is really big, but it's only for display purpose that these arrows are multiplied. Their length is multiplied by 25. So uh, actually, that's how it would look like if I displayed them in a normal units. And here in the right side, in the results and statistics, we have numerical values for this error. And yeah, I see that the error is quite big. Average error is almost 2 pixels, with maximal being 10 pixels. That's a lot. And I should do better with my calibration board, but I will not do it now. Let's leave it just as it is. Just I want you to remember that you can find all statistics and errors that come from the calibration itself. It's not a measurement error that you can expect at the end of your application, because there are many different aspects that will contribute to that. But this is the error that comes from the calibration itself. And now I have my camera intrinsic parameters calibrated. Let's go to the next step. World to image transform, or whatever you call it, perspective calibration, real world calibration. That's the second step, where I will use a single image from perspective calibration folder. So different camera position here. And actually, in this step, we can enter points manually if you would like to, just by clicking on the image and giving coordinates in the real world units for the points that you manually select. But we will use calibration grid, which is a circle grid, and let's measure circle radius on this image. It's basically the same. Let's leave it on 30. We need also, or we don't have to, but we can specify circle spacing in millimeters. and I see on the board that it's 10 millimeters. So let's use it. And click locate. All circles were successfully located. And that would be enough to calibrate perspective, to remove perspective distortion and lens distortion from this image. But if I want to convert units from pixels to real world units, to millimeters, for example, I can specify starting point of the new coordinate system. That's especially important in applications with the robots, because at this step I will specify a 0 point and axis direction for real world unit coordinate system. And that's the same coordinate system that robots should be calibrated in. So I will pick one point on the calibration grid. So, for example, this corner. And I will specify its real world coordinates as 0, 0. Then I will select another one, and I will say that this is my y-axis. So coordinates of this point should be 0, 10, because 10 millimeters is spacing of my calibration grid. And this point will set direction for x-axis. So coordinate system, coordinate of this point is 10, 0. I specified real world coordinates for 3 points that will establish 0, 0 point and axis direction for my real world coordinate system. And now I can compute world transform. Okay, I see also some results and statistics about the error here, but let's click next. This is just a finalizing step. I will add also an image here, and it will be the same image as in previous steps, so perspective calibration image. And I will generate rectification map. Okay, and that's my image after rectification. So as you can see, we removed perspective distortion. We removed also lens distortion. It's not as easy to spot that there was some lens distortion, but if you take a look here, I don't know if it's visible. That's closer to image edges we are, the more bent are our lines. So straight line in the middle of the image would look as a straight line, but the closer we are to the edge, the more bent it would be. That's barrel distortion, which is result of the lens, which is parameter of the lens, and calibration could also help to reduce this distortion. Anyway, that's our transformed image, rectified image, and we can approve it by clicking OK. Okay, so that's basically it. That's basically calibration done. Now let's make some use of it. Let's just for quick testing, let's measure distance between two circles on calibration board. We know that this distance should be about 10 millimeters, and let's check if our calibration is precise or not really. I need fit circle, which you already know, fit circle to edges, and I am linking rectified image. So image from rectified image filter, and I am specifying fitting field. I will pick some of the points in the middle of the calibration board because I expect that results will be better in the middle than on the edges. And polarity is dark to bright. Okay, so which one is it? 3, 4, 5, 6, 7, 8. 6, 7. Okay, and another fit circle. I will add to my outputs circle centers. And it may not be intuitive, but if I measure the distance between the circles or centers of these circles right now, it will not be yet in millimeters. Let's try. Point to point distance and circle center to circle center. That's connecting segment. So our measurement line. And that's our distance. So it's still in pixels. To convert this measurements to measure in real world units, we have to use image objects to real world filter or to world plane. Yeah, image objects to world plane. And I will transform just this circle centers, just the points. As a transform, I have to link my rectified transform and one circle center, the same for the other. And now I can measure again. So point to point distance, world point 1 to world point 2. And this is not exactly what I expected. I must have made some mistake here when specifying these coordinates. Let's try again. Okay, so it's not using this anyway. Okay, I will have to explain this later on. I will get back to you with. Okay, I see answer in the chat. I changed my Y direction and now it's okay. Yes, I also have seen that before, that if we do this, then everything is fine. So computed grid spacing is now 10 millimeters as it should be. And before this operation, uh, computed grid spacing is 5 millimeters. Just it doesn't make sense. Let's use inverted y-axis for now. So let's use it like this just to have accurate results. But the other option with not inverted y-axis, in my opinion, should also work well. And I will explain it. And give you explanation tomorrow. For now, let's just continue. Generate rectification map. Yep. Sorry. Okay. And now results are as expected. So 10 millimeters from one circle center to other circle center. As you can see, calibration and image rectification can be quite difficult topic. Um, Please remember that whenever you struggle with a tool, with some filter algorithm from our library, you can jump directly to help page for this particular filter by selecting it and pressing F1. So here I've got help article about rectify image filter. And if that's not enough information, I have also links to other related articles, examples, and tutorials. For example, this one. You will find information here about how to perform this operation, and also about the other approach using different filters. So instead of using uh, this editor, instead of using this simple step-by-step editor, you can use filters like calibrate camera pinhole. Yeah, this is a single filter, single tool for calculating camera intrinsic parameters, and the next steps of the process uh, with calibrating world plane and so on. I generally recommend using editor for calibrating camera because it's the simplest possible method, but you can read more about other filters for this purpose. Are there any other questions? In case anything comes to your mind later on, we can discuss everything tomorrow, because that's the last thing that I wanted to do with you today. Tomorrow we start the same as today, so 8:30 my time. I don't know how it's in your part of the world. Uh, and yeah, we will tomorrow we will focus more on the program structure. Today, we covered basic vision algorithms, basic tools, which are building bricks of our program. Tomorrow, we will learn how to use them all together, how to build structurized program with different subroutines, with different loops and either separate threads running independently. We will cover also communication, TCP/IP communication, how to send our results outside. Uh, we will also cover some of the 3D tools, and hopefully we will have also time for a Q&A session at the end of tomorrow day. So please prepare any questions that are not related to program that we are building during the training, but questions more general, maybe about your applications that you are struggling with or you would like to test in the future, or any other general questions about the software. So please prepare them for tomorrow, even if you have some sample images from your applications that you would like to work on together during the training. We can also do it. I hope that we will find the time at the end of the day tomorrow. Okay, thank you for today. See you tomorrow. Bye bye.